If A and B are two vectors, if we are to find the component of vector A on vector B, there's a formula that helps us to do that. And the formula says that the dot product of the two vector A and B will have to be divided by the magnitude of the recipient vector, and that is vector B, which simply means that if you are to find the component of vector B on vector A, you will still need to find the dot product of the two vectors, but in this case, the recipient vector is simply vector A, and that will be the magnitude of vector A. Now, what if it is the projection? To find the projection of vector A on vector B, the formula is a little bit different, but they actually have similarity, and that is in terms of the dot product. You will still need to find the dot product of the two vectors, but in this case, you are dividing by the square of the magnitude of the recipient vector. That's not all, as you will need to multiply by the vector itself, B, which simply means that if you are to find the projection of vector B on vector A, we will need to find the dot product of the two vectors, divided by the square of the magnitude of vector A, and multiply it by the vector A itself. Now, you might be wondering, where are these formulas? Where are they coming from? How can we show them out? Let's try to prove them out. Consider two vectors A and B inclined at an angle theta to each other. If this is vector A and this is vector B, then the angle between them will be somewhere around this region, and I'm going to denote that with theta. Now, if a ray of light is formed somewhere around this region, notice that it's going to reflect on vector A, and vector A will cast a shadow on vector B, which will be along this direction. Now, what can we draw out from this conclusion? You notice that this line and this line is now serving as the component of vector A, which simply means that we can determine their magnitude. So what I would like to do is to assume this point is point O, this is point N, and this is point M. What if I want to find the length of OM? What would I do? What do you think? Well, you notice that we are having a right angle triangle, which means we can always use some of the trigonometric functions. And what functions do you think will help us to determine the length of OM? You notice that the cosine function can always work out. What says the cosine of angle theta? It says that we should find the ratio of the adjacent, which is OM, divided by the hypotenuse, which is the magnitude of vector A itself. And if I solve for the length of OM, at the end of the day, we should have OM to be equals to the magnitude of vector A itself multiplied by the cosine of angle between them. So let's keep that aside. I would like to call it equation 1. Well, let me just put 1 over here. Now let's recall what says the dot product of two vectors. If we find the dot product of the two vectors A and B, this is simply the same as the magnitude of A multiplied by the magnitude of B, then multiplied by the cosine of angle theta. The expression at the right hand side can be rearranged as the magnitude of vector B multiplied by the magnitude of vector A multiplied by the cosine of angle theta. You notice that what we have right here is quite similar, even the same as what we have over here. So eventually we can make substitutions. So I would like to replace the magnitude of A multiplied by cosine theta with the length OM. And therefore, we can have the dot product of the two vectors AB to be equals to magnitude of vector B multiplied by the length of OM. Now, I would like to isolate OM by dividing through by the magnitude of vector B. And so therefore, the length OM is simply equals to the dot product of the two vectors all divided by the magnitude of vector B. The process of finding OM is what we call the scalar component of vector A on vector B. And this is the formula that helps us to do that. And that is where the formula is coming from. So now you know how the scalar component formula is being derived. So the only difference is that you have to be very sensitive about those vectors. This statement corresponds to this formula. However, it can be in other way around. So what am I referring to in Excel? Sometimes you might be required to find the components of vector B on vector A. You don't have to be panicked. You will still find the dot product of the two vectors. But in this case, you will need to divide it by the recipient vector, that is the vector that they are casting shadow on. So that will be vector A. So magnitude of vector A. So that's something you want to always be very, very careful of. And that is how the scalar component formula is being derived. So now what about the vector projection formula? Let's try to look into that. Now, instead of finding the magnitude of OM, what if I want to find the vector OM itself? What would I do? What do you think? Pause the video and think of what we can do. To have enough space, I will need to get rid of some stops. Hopefully, you have written that. Perfect. To determine vector OM itself, we need to understand some of the properties of parallelism of vectors. You notice that vector OM tends to be parallel to vector B itself. So therefore, vector OM will be equals to the magnitude of vector OM, then multiplied by the unit vector of B. Why? Because vector B seems to be much more larger in terms of magnitude to that of vector OM. So to determine that of the corresponding coordinate, that is the corresponding component of vector OM, we need to multiply its magnitude by the unit vector of vector B, since they possess the same unit vector. It's one of the properties of parallelism of two vectors. So it's something you want to keep in mind. So if that is the case, what says the unit vector of vector B? To determine the unit vector of any vector, that's simply the same as the vector itself divided by its magnitude, B. But earlier, we were able to determine the magnitude of vector OM. And we got that to be the dot product of the two vectors, all divided by the magnitude of the recipient vector. So that means we are almost there. We can now determine vector OM itself by just replacing the magnitude of itself by this, and that of the unit vector of B by this. And therefore we have A dot B divided by the magnitude of B itself, then multiplied by B itself divided by the magnitude of B again. So can we simplify this forward? Yes, we can. So at the end of the day, we can have the dot product of the two vectors divided by the magnitude of B all squared, then multiplied by vector B. And this is how the formula of the projection is being derived. So you have to be very, very careful. If the question talks about finding the scalar component of a particular vector on another vector, you have to use this formula right here. But if it talks about the vector projection, that is, they want the answer in terms of vector, so definitely you have to use this formula. And that is the difference. So let's try to put it in practice. Hopefully you got that. Consider vector A to be equals to the following components: 1, -2, -2, and vector B to be equals to the following components: 6, 3, and 2. Pause the video and find the scalar component of vector A on vector B, scalar component of vector B on vector A, vector projection of vector A on vector B, and the vector projection of vector B on vector A. Pause the video and figure this out. So let's begin with the first one. What would be the scalar component of vector A on vector B? Well, I think there's something I would like to disclose. There's a way in which this can be written as well. Some textbooks might write it as this. Yes, it can be written as this. That is vector A on vector B. Okay, but in most cases, it's always being simplified out so that you can know the difference. Because those textbooks, they make use of that for projection, similarly for components. So how we know what to do. But in most cases, it will be simplified out. Okay, that's just something you want to keep in mind. So the component of A on B will be equals to the dot product of A and B divided by what? Divided by vector B, because vector B is a recipient vector. So divided by the magnitude of vector B to C. So what is A dot B? To find A dot B, you just need to multiply those components respectively. Okay? I hope you get that. So 1 by 6, 1 times 6 is 6, plus -2 times 3, that's -6. Then -2 times 2, that's -4, plus -4. Then I'm dividing that by the magnitude of B. What would be the magnitude of B? Let me determine that over here. To determine magnitude of B, that will be the root of the sum of the square of each of those components. And that will be the root of 36 plus 9 plus 4. And that will be the root of 49, which is the same as 7. Perfect. So I'm dividing this by 7. Let me use different color, so you will misquote them. So now we can conclude our answer. So this cancels out. Then we should have -4 all divided by 7. And this is the scalar component of vector A on vector B. So what about the scalar component of vector B on vector A? Well, I would like to suggest that you do that yourself, just to practice. So I will just move to the third one, the projection of vector A on vector B. To determine the projection of vector A on vector B, earlier we were able to derive the formula, and the formula says we have to find the dot product of the two vectors. We should divide it by the square of the magnitude of that recipient vector, and finally we should multiply it with the vector itself. So we got the dot product earlier to be -4. Oops, I hope you can remember that. And magnitude of B, we got that to be 7. So I'm squaring that. Then B itself is 6, 3, and 2. So that will be -4 all divided by 49. Then multiply by 6, 3, and 2. If you want, you can distribute this magnitude as a scalar to each of these components respectively. And if you don't want, you can just leave it like that. Your lecturer or teacher should mark it that way. And that is it. I will give this to you as well. Put that in practice. And let me know your solution in the comment section below. Hopefully you find this content helpful. If you haven't subscribed, do well subscribe. Thanks for watching. See you guys in the next video. Bye for now.